Hello everyone. Welcome at the Data Platform Virtual Summit 2021. This is the session, now where did that estimate come from? And if you're wondering, what estimate? Well, we are not going to talk about these types of estimates or these types of estimates. But these two pictures do show why estimates can be important and why estimation that goes wrong can be dangerous. So we are going to talk about these kinds of estimates. And if you have seen such things in your execution plans before, you know that if the actual number of rows and estimated number of rows in an execution plan are that far off, that can often be a root cause of bad performance and bad execution plan choices. So in this session, we are going to dive into where those estimates come from. We're not going to tell you just how to fix it, but a lot of ways to fix it become obvious once you know where it comes from. So the idea is to make you understand how the estimation process works. It's a deep dive session. We will start easy, but the level will go up very high eventually. My name is Hugo Kornelis and I make SQLServerFast.com. SQLServerFast.com is the website where I built the execution plan reference. The execution plan reference is a project I started because I love execution plans. They are the best thing in SQL Server to give you insight in why queries run slow or why they run fast. But Microsoft doesn't document them very well. The documentation that is out there on the Microsoft websites is limited. It's often outdated. It's sometimes just incorrect. And there are huge gaps. So that's why I decided to build a complete reference website with full information about everything in the execution plans. Also on SQLServerFast.com is my execution plan video training, a huge collection of videos, still growing, planned to be over 24 hours of content. That will take some time before I have that completed, with in-depth training on how to read and work with execution plans. Because I always am happy to have people in my sessions, I like to give something in return. So starting today until the end of October 2021, if you decide to purchase access to the execution plan video training, you can use the code DPS 2021 to get a 10% discount on the purchase price. I also have a lot of other content on SQLServerFast.com, like my blog, like some articles, and very important, I have an area called resources, and that's where you can find the slide deck and the demo code of this presentation. I also do a lot of other stuff, I work, etc., but you don't care about that. What you do care about is my email and my Twitter. Maybe while watching this session, you don't have questions at that time, but they come up later. Mail me, tweet me. Maybe you didn't catch this session live and you are watching it in the recording, and you can't ask me because it's a recording. Mail me, tweet me. I love to help people get a better understanding of execution plans and other areas related to SQL Server query performance. And I always like to help the community. So if you mail me and I don't reply within a week or so, then I am not deliberately ignoring you. I probably just overlooked your mail in the swamp of other mail. So just send me a gentle reminder. Hey Hugo, I sent you this mail last week. Did you already have time to look at it? And I will get back to you. Now we are going to talk about cardinality estimation in this session. And for the record, this is a 2-hour session. So it is a longer, more in-depth version of this presentation than if you have seen it in other places where I have delivered it in 1 hour or 75 minutes. Also, this is a recording, so I cannot answer your questions live, but the benefit of it being a recording is that right now, as I am talking, the several months old version of me, a live version of me is also watching, is in the chat. So if you have questions, you can just type them in the chat and I will answer them in the chat. At the end of the session, there will also be approximately 15 minutes left for live Q&A. And of course, like I already mentioned, after that you can always mail and tweet me. We are going to talk about cardinality estimation, and if we are doing that, it is important to realize that the logic behind the cardinality estimator has changed significantly in 2014. So we have two versions of the cardinality estimator. The old version that was introduced in SQL Server 7.0 and was not changed in any way until and including SQL Server 2012. And then there is the new cardinality estimator that was introduced in SQL Server 2014 with significant changes. And then after that, Microsoft made some small improvements and changes in later versions. In this talk, everything I'm going to say and all the demos will be based on SQL Server 2014, except where I deliberately also reach out to describe the old cardinality estimator behavior as it was until SQL Server 2012. Now, if you have two versions of the cardinality estimator, the question is, of course, which one is better? Now, the problem with estimations is estimations are not exact. They are by default, by definition, estimations. Estimations are bound to be wrong. And the new cardinality estimator made different choices in how it estimates, but it's still estimations. So if you change your choices, you change your results, but they will still be wrong. They're just wrong in different ways. So you can't really say that the new cardinality estimator is better or the legacy cardinality estimator is better. Both of them are wrong in some cases. They are just wrong in different cases and wrong in different ways. And which one is better depends on your workload. Which kind of error hurts you the least? That's basically the question you should ask. And then the good thing is, if you are on SQL Server 2014 or above, you actually have both versions available. Microsoft never removed the code of the legacy cardinality estimator. It is still there. And that means if you are on SQL Server 2014 or above, you have your choice. You can change your database compatibility level, which changes a lot of things, but also changes which cardinality estimator version is used by default. But you can also, on an individual query basis, override that behavior by using option query trace on and then 2312 or 9481 to force the new or force the old cardinality estimator. Of course, you only need to force the new if your default is to use the old, so if your compatibility level is SQL Server 2012 or below, and you would only force the legacy behavior if you are on compat level SQL Server 2014 or higher. Unfortunately, query trace on option requires rather deep permissions, and a lot of people were uncomfortable giving those permissions to their regular users. So as of SQL Server 2016 and higher, there are more versions like alter database scoped configurations, set legacy cardinality estimation is on or off. And I forgot to add it to the slide, but in SQL Server 2017 or 2019, more options were added. And as I say this on the recording, I will type in the chat what the exact things are, what version and what options there are to better control which cardinality estimator version is used on a per query basis. So we are going to talk about cardinality estimation. And we start with what is cardinality estimation, how is it done, why is it done, and how is it done. And the how is it done will be the main part of the talk. And in that part we will start with the usual suspects. Those are a list of relatively well-known issues with cardinality estimation that I'm going to touch on just to be complete. After that, I will explain what statistics are and how they are built and how you should read them. And then we will see how those statistics and other things are used to estimate cardinality in first single table queries with simple filters or with more complex filters. And then the last part of the session is where it really gets exciting and interesting, but where the level really goes high. That's where we will talk about cardinality estimation in queries that use multiple tables. So we have joins. And then we will talk about cardinality estimation if there's just a single equijoin, or a single non-equijoin, or even multiple join conditions. All of that should be enough to make your head spin. Luckily, there is a recording, so you can always return to it later and review it later. Let's get started. What exactly is cardinality estimation? Cardinality estimation is a prediction for each operator in an execution plan of how many rows it will return. But it's a prediction, it's an estimation, it's bound to be wrong. I know I've said that before, and I will say it probably a few more times because it's very important to realize cardinality estimations are bound to be wrong. Our goal can never be to have them always exactly correct, because then we are not estimating, and the only way to get them exactly correct is to execute the query. The idea of cardinality estimation is to get as close as possible in a very short time. So yes, they will often be wrong, and we are only concerned when they are too much wrong or when the type of wrong affects us too much. So cardinality estimation is a prediction of how many rows an operator will return. On your screen, you right now see an example execution plan. In this execution plan, you can hover your mouse over one of the arrows and you will see a pop-up that shows, in this case, an estimated number of rows of 1. Now, it is important to realize that when you hover your mouse over an arrow, you are not looking at the properties of that arrow, because the arrow doesn't actually exist in an execution plan. The arrow only signals how data is transported between operators because of how operators call each other. In the case of the arrow here, nested loops is the operator that calls clustered index scan. Clustered index scan responds by returning rows, and the estimate is that it will return 1 row. This arrow is not part of the execution plan. It's there as a visible clue in the graphical execution plan, and the properties you see there are actually properties of the right-hand side operator. So if you hover your mouse over the clustered index scan, you will see that same number of 1 estimated number of rows with the same estimated row size and data size, plus a lot of other properties. The reason why Microsoft built it this way is that if you hover over an arrow, you just get a subset of properties that are relevant for the data to be returned, instead of all the properties that are relevant for the operator. You should be aware what you are looking at. Now, you can hover your mouse over any operator or any arrow in the execution plan. For instance, if you do that on the arrow between sequence or stream aggregate or on the stream aggregate itself, you will see that stream aggregate is estimated to return 1.02069 rows. Well, here we already know in advance this estimate will never be correct, because there are no fractional rows in real life. Row exists or it doesn't exist. But this is the reason why this happens, is because cardinality estimation is a mathematical process. It uses formulas to approximate the numbers, and that results in fractions. You could see this as probably 1, but a small chance of 2. But it's basically just a number SQL Server uses that tries to be as close as possible based on mathematical formulas. So you will often see fractional rows in those estimations. Don't worry about it. It's a good reminder that they will never be correct, and they don't have to be correct. If you hover your mouse over the select operator, or whatever the top left operator is called, you will also see an estimated number of rows, and that's the estimate of the number of rows to be returned by the entire execution plan. Now, all these numbers are computed by the cardinality estimator following logic that we will talk about later. But why is this important? Why is the cardinality estimator doing all that? Well, to understand that, let's sorry. The reason it does it is because those cardinality estimations are useful to help determine plan choice. So how does this work? If you look at the number of rows estimated to be returned from the nested loops to the sort operator, that's also the same number, 0.12169 in this case. That number is very relevant because that number is the number of rows that is the input for the sort operator. And sorting 1 or 2 rows is a completely different beast than sorting 1,000,000 rows. The cost of the sort operator, or rather the estimated cost of the sort operator, depends on how many rows it has to sort. And the same goes for all operators. For many operators, the cost scales linearly. Process twice as many rows, it takes twice as much effort. For some operators, it's different. Some operators have a more exponential scaling. Sort actually has a very exponential scaling. There's also operators that have more logarithmical scaling. But bottom line is, every operator knows how to compute its estimated cost from the estimated input cardinality. And those estimated costs are computed for each operator, then added together. And if you look at the select or other top left operator, you will see an estimated subtree cost there, which is the sum of all the estimated operator costs of all the operators in the execution plan. This number is the estimated cost for this execution plan. And this is important because when the query optimizer tries to determine the best way to execute a query, it will consider hundreds, perhaps even thousands of possible execution plans. And for each of them, it will go through the steps of predict how many rows there will be, compute the estimated cost, add it all together for the estimated cost of the entire execution plan, and that helps it pick the execution plan that is estimated to be the cheapest. The way I describe it is very inefficient, and in reality there is some optimization, but there is still a lot of work involved in coming up with a plan choice, because it does need to have the estimated cardinalities and estimated costs for all relevant operators in all relevant plan considerations. And for the chosen plan, we can see the results in the execution plan. So if the cardinality estimates are wrong, if the actual number of rows that is input to the sort operator turns out to be 5,000 and not 1, then perhaps bad choices were made. Perhaps the nested loops operator was a bad choice. Perhaps a merge join or a hash match join would have been a better choice, and perhaps that choice would have been made if the correct estimate had been determined. Perhaps we chose the wrong index. Perhaps based on knowing how many rows there are, if the estimate had been better, a different index had been chosen. Perhaps we should have parallelized this plan if we had known in advance how many rows it would process. But for just 1.02 rows estimated, you're obviously not going to do a parallel plan. But if the real number of rows is millions, a parallel plan might have been much better. So all those choices are all based on the cardinality estimation. If the cardinality estimation is wrong, those choices will be wrong and you can get slow queries. The memory grant is also determined by the cardinality estimation. In this sample query, we have a sort. A sort needs to store data in memory. That memory needs to be pre-allocated. So in the execution plan, in the select operator, you can see that the memory grant in this case is 1024 kilobytes. That's really small. Why is it really small? Because we expect to sort somewhere between 1 and 2 rows. Storing 1 or 2 rows in memory doesn't take much memory. If in reality we need to store 1,000,000 rows there, 1024 kilobytes will never be enough. And we run into bad issues. So there are some operators that store data in memory. I mentioned sort, hash match join and hash match aggregate are 2 other examples. Those are the 3 main ones. And what happens is that the memory grant is computed, and that is based on the cardinality estimates and totaled for the entire execution plan. Now, if you execute a query, SQL Server will first assign and reserve that memory. So if your memory grant is very high, you are reserving a lot of memory, and that reservation may take some time if your server is busy. If the memory is not available, your query will wait until it becomes available. Then the memory is reserved and nobody else can reserve it. So if your memory grant is much too high, you run the risk of having to wait until your query can start because it wants to reserve all that memory, and you run the risk of making other users sad because now you are hogging all the memory even though you don't need it because the memory grant was too high. But the flip side of the coin, if your memory grant is too low, then operators will run out of memory. And if an operator runs out of memory, it will need to spill to tempdb, which means a much slower execution because now there's physical I/O involved. And we switch to an algorithm for tempdb instead of an algorithm optimized for in-memory, which also is slower. So there are lots of reasons to want the memory grant to be as good as possible, which means your cardinality estimation should be as good as possible. Now, there are a long list of things I call the usual suspects, the most common and most well-known reasons for bad cardinality estimation, and I'm going to go through them fairly quickly. So one of them is table variables. Table variables are not bad. Table variables are good. They have benefits over temporary tables, but they also have drawbacks. There is no simple choice to say I should use a table variable or I should use a temporary table or I should use a fixed table. There are reasons for all of them. But one thing with table variables is they have no statistics, which is beneficial because it means they never update, they never cause or recompile. But it also is a downside because it means it's much harder to estimate cardinality if you don't have statistics. The estimated cardinality of the entire table is always one row, except that it's not always one row. People always say it's always one row, but that's wrong. It's often one row, but not always. And I will show you later in the demo some cases where it's not one row. I will also explain why it isn't always one row and why it often is one row. Now, if you run into issues because of this, and like I said, table variables can be the correct choice. You don't always run into issues. But if you do run into issues because of this standard, usually one row estimation, you can use a temporary table instead, which has other benefits but also other downsides. Or if you're on SQL Server 2019 and you have the compatibility level of SQL Server 2019, a new feature called Table Variable Deferred Compilation will kick in, which might help you, or again, might hurt you. That's a bit beyond the scope of what I'm going to talk about today, but know it exists and make sure that you understand it if you are running SQL Server 2019 and using table variables. A similar and related issue is in multi-statement table-valued functions. If you use multi-statement table-valued functions, you are calling a function that fills a table, an internal table variable, and then uses that in the main query. So it's implemented under the covers using a table variable, which means it has the same issue of no statistics, and the estimated cardinality at first was always one row. Specifically for multi-statement table-valued functions, there was a fix in SQL Server 2014 where the hard-coded one row estimated cardinality was changed to a hard-coded 100 rows cardinality. Now, is that better? I don't know. In some cases it might be better. In other cases it might be worse. Whatever number you put there, as long as you put a hard-coded number there, and there is a reason is there, and I will explain that in the demo. There is a reason why there had to be a hard-coded number there, but any hard-coded number you put there is always going to be wrong, is always going to give you issues if the real number is different. Now, if this causes you issues, you can try to rewrite the multi-statement table-valued function as an inline table-valued function. That requires that all the logic is in a single select statement. So it can be hard, but it can be very beneficial. I talk about that in other presentations. It's not in scope for today. Or you can, if the query allows it, execute the multi-statement table-valued function first in a separate query with a select into a temporary table, and then use that temporary table in the function. That is not always possible. It depends on how the multi-statement table-valued function is used. But if it is possible, it might help. And on SQL Server 2017, interleaved execution is a feature that basically does that copy to a temporary table under the cover for you. Again, read up on it if you are supporting SQL Server 2017 and if you have multi-statement table valued functions. It offers some relief in some cases. It's definitely not a good fix, and I personally still think that multi-statement table valued functions should be avoided in almost all cases because of issues like this, and interleaved execution doesn't do enough to fix it. But often you inherit code or have code that does use it, so it's important to know about it. Let's jump into a demo and look in a bit more detail at the things I've talked about. So let's first execute the demo that prepares the database, and in this code, I'll show it what I do. I create an estimate demo database and I use some dynamic SQL to make sure it goes in the same directory where your master database is. That might not be where you want your databases, but I set up my SQL this way so that it can be sure that whoever is going to execute it on whatever system, it's always going to go to a directory where SQL Server that exists and where SQL Server has write permissions. But you can of course change this. And I'm going to create some tables and I'm going to fill those tables from the AdventureWorks sample database. So you need to have the AdventureWorks sample database there. What I do is I create a copy of sales order detail, but I actually do it 3 times to have more data because I want a larger data set. And then I do an update statistics with full scan. We'll talk about the statistics later, but here you will see that the statistics should be as good as possible. After that, I delete 5% of the data so that now the statistics are not perfect anymore. I do that deliberately because on real systems, your statistics are often not perfect. Rows may have been added, rows may have been deleted. And then I create a second copy of the table that is exact same as the first one, but has only the remaining 95%. And for demo table 2, the statistics will be perfect. So this simulates what demo table 1 would be if we do another update statistics after the 5% delete. Now, I will use this demo database in some of my examples. I will use AdventureWorks itself in some other demos. And in this case, I'm going to use the AdventureWorks demo database itself. So I will return to this database we just created later. But first, let's make sure we're in the right database. And let's look at an example with a table variable. Now what I do here is I declare a table type. And then I declare a table variable, insert rows in it. That's just the setup, but I do need to do this all in a single batch because it's a variable. And then I run 2 queries, and the queries are really not important. The results are not important. I only want to look at the execution plans to see the estimations, because we're going to talk about cardinality estimations today. So I don't care about the results. We are going to talk about the estimations only. So I have basically the same query, once normally and once with the option recompile. And let's execute this, and it helps to enable the execution plan option. Let's execute it again and go to the execution plans to see the results. The first query is the filling of the table variable. We're not going to look at that. We're going to look at the 2 queries. Let's just make sure that only those are in view. We're going to look at the 2 queries that get data from the table variable. The first one reads from the table variable and it has an estimated number of rows of 1. I told that before, using table variables gives you an estimate of 1. However, if I hover the clustered index scan of the second execution plan, you will see that now the estimated number of rows is 290, which actually is a perfect estimate because the reality is also 290. So we already see that the estimate is not always 1. And that has to do with how the logic of the cardinality optimizer works. If you look at the highlighted batch, this entire batch is offered to the cardinality, to the query optimizer at once. And the query optimizer will go through this entire batch and create execution plans for all queries. So it will create the execution plan for this query, but not execute it yet. It's only creating the execution plan, then create the execution plan for this, and then create the execution plan for this. For the last two, it uses a table variable as part of the preparing. The declare statement has already been passed, so the optimizer knows the structure of the table. But the insert statement has not been executed yet. We only have the execution plan for it, but we haven't run it yet. So it's an empty table variable at this time. And if SQL Server looks at the data it has on the table variable, well, there is no statistics, but it does have information about the cardinality, and that says it's an empty table. So the estimate is 0. Now the query optimizer doesn't like 0. The query optimizer only uses an estimate of 0 if it has 100% certainty that there is a fallacy in the query, so there cannot be any rows. If there is a theoretical chance of rows, even if based on currently available data there are no rows, if there is a theoretical possibility that there might be rows, the minimum cardinality estimation is always 1. And that's why this execution plan gets an estimate of 1. And by the way, this execution plan also gets an estimate of 1. But Hugo, you just showed us that it was an estimate of 290. Yeah? Wait for it. At this point, the execution plan that is returned will have an estimate of 1. And then all the 3 execution plans are there, and now execution starts. This query runs and adds 290 rows to the table variable. Then this query runs, and as we saw, it results in an execution plan with runtime statistics that says we estimated 1 row, but in reality there were 290. But then the last query runs, and this query has an option recompile, which means just before you execute the statement, you have to recompile the plan for only this statement. So the plan we had before, with an estimate of 1, is not used. SQL Server will again create an execution plan. And there are still no statistics on my table, but SQL Server does know at this time that there are 290 rows there. And that's why we get an execution plan for 290 rows and not for 1. Now, in this case, that means that we always get a correct estimate. But this similar process also has some weird results. So let's do some setup. I'm going to create a table variable type. Not many people know it can be done, but here is how you do it. Then we're going to create a procedure that has a variable input that is of this type. So this means that we're going to pass a table variable into the procedure, and the procedure itself is very simple. Let's make sure it exists. And now we're going to do something interesting. We're going to declare a table variable as that type. Then we're going to add some data there, and then we're going to execute the procedure. Then we're going to delete some data from the table variable, and we're going to execute the procedure again. And now I want you to look at the execution plans you will see and the table cardinalities. So the first plan is again for filling the table variable. The second is the first execution of the procedure. And now we see that even though there is no recompile, we still have an estimate of 290. The reason here is that SQL Server creates execution plans for this batch before it starts executing. But it only has an execution plan that says, I need to execute a procedure. When it actually runs this execute dbo.countum, that's when it says, oh, I need to fetch a procedure. Oh, I don't have an execution plan for it yet. So at this time, it will create an execution plan for the procedure, which uses this in table. And similar to how stored procedure compilation sniffs the values of normal variables, it will now sniff the cardinality of a table variable. Because at this time, the execute runs after the insert has run. So it compiles the procedure when this table already has 290 rows. And that means that we get an execution plan based on 290 rows. Now after that, let's return to the execution plans. We have an execution plan to delete 100 rows. So now there should be only 190 rows remaining. And then we execute the store procedure again. Whoops, let's make sure it's there. And now you will see that execution plan still is based on an estimate of 290, and actual number of rows has been reduced because we deleted 100 rows. So now you see that just like with variables, with parameter sniffing for regular parameters, table value parameters get their cardinality sniffed, and also again the execution plan is stored and reused, and it's not recompiled every time. So this is a similar process to parameter sniffing. So that's how you work with table variables. Now I'm also going to show an example with a multi-statement user-defined function. So I'm not going to talk about the content. This is a multi-statement table valued function. I'm going to drop and create it, so make sure it's there. And now I'm going to run a query, and this query will use this multi-statement table valued function as one of the inputs, but then join to something else. And let's just run it and make sure that we see the execution plan and statistics results. Now, if I look at the execution plan, you will see an operator called table valued function. This is where the table valued function is invoked and adds data to an internal table variable. And then you will also see a clustered index scan that actually reads from that internal table variable. It has the same name as the function, but it is an internal table variable. And what we see here is that the estimated number of rows is 100. The actual number of rows is higher, it's 290, but the estimate is 100. So here we see that the estimate is 100, not because that is an estimation of reality, it's just hard-coded. Also, if I enable query trace flag 9481, I force SQL Server to use the legacy cardinality estimation. So now we pretend we're on SQL Server 2012 and before. And as I already said in the slides, that means that we now have an estimated number of rows of 1. And this is simply the standard logic of, hey, I am reading from a table variable, an internal table variable that's empty at the time I create the execution plan. So the minimum estimate is 1. The 100 is actually a specific exception that was hard-coded into the product in SQL Server 2014 to alleviate some of the worst problems. Now, when I talk about worst problems, let's take a quick look at the set statistics IO option. So what we see here is that a relatively small table, employee department history, has been scanned 290 times, resulting in 582 logical reads. This entire table is, I think, 3 or 4 pages. It's a very small table. I don't have the exact number, but it's read 290 times and it's scanned 290 times. Why does SQL Server do that? Because the estimate says, let's break this down, because the estimate says, based on 1 row returned here, I will only execute this 1 time. And if I execute it 1 time, a scan doesn't hurt. But in reality, it executes 290 times. With a better estimate, we probably would have had a better execution plan and better performance. Okay, let's return from the demo to our presentation and go through a bit more usual suspects. So another very common cause of bad cardinality estimation is stale or outdated statistics. We'll talk more about statistics later, but if your statistics are outdated and stale, then they no longer describe reality. You want your statistics to be current and realistic and representative of how your data looks now, not of how your data looked 2 years ago. So if this is something that's giving you options, giving you issues, consider the auto update statistics setting of your database. It should be on by the default out of the box, and you should keep it that way. Do not disable this unless you have a very specific reason to, and if you disable it, make sure to set up manual update statistics logic, because otherwise they will run stale and outdated. I mentioned here the auto update statistics async option. I like that option very much, because if it's disabled, which is the case by default, then as soon as a threshold is hit, the next time a query is using that statistic, SQL Server will first update it, and that means there is a delay. That threshold is not a magic number where you're guaranteed to get problems. So I like the async behavior where as soon as that is hit, when a query is executed that uses it, SQL Server says, oh, this statistics is outdated. I'm going to kick off an asynchronous process to update it, but I'm not going to wait for it. I'm just going to execute based on the old statistics anyway, because when we were 2 rows below the statistics, you weren't complaining. 5 rows above the threshold, you probably won't complain either. A very important trace flag to be aware of, and I personally enable it on all instances I have, is trace flag 2371. It was introduced in SQL Server 2008 R2, and it is, like I said, I personally enable it because I consider it a required trace flag on instances until SQL Server 2014. In SQL Server 2016, it's actually enabled by default, and you always get the new behavior if you have compatibility level 130. So trace flag 2371 affects the threshold for statistics updates. Without trace flag 2371, the statistics, the threshold is 20% of your table. So if you have a table with 10,000 rows, 20% is 2,000. It will only update the statistics after 2,000 changes, 2,000 rows have been changed in that table. If you have a table with 1 billion rows, that means that it will wait until there are 200 million rows changed. If the table happens to be your last 10 years of sales data, and your sales amount doesn't change significantly over time, that means it will probably take 2 years before the statistics are automatically updated. And you spend 2 years on very outdated statistics. Microsoft realized that, especially for very large tables, this 20% was not a good choice. And that's why trace flag 2371 was introduced, where for larger tables, and that's the red line in the graph you see on screen, for larger tables the threshold goes down. What you see on the screen is the threshold as a percentage, not as a number of rows. The number of rows still goes up, but it doesn't go up linearly anymore. That means that for larger tables, you don't have to wait 2 years or 3 years between update statistics. You get them more often, which is much better for your behavior. Then there's also an issue with unrepresentative statistics. Statistics are limited in what they can represent, especially if you build them with a low sampling rate. Using a low sampling rate means SQL Server looked at only a few pages in your table to quickly get the statistics. If you use a higher sampling rate, it will look at more pages. If you use full scan, it will look at all pages. That's slower. It uses more resources. There is a reason to use a low sampling rate, especially on large tables. But if you look at more pages, you probably get more representative statistics because you see more of the data. If you use automatic statistics update, you cannot configure the sampling rate, so you are limited there. For manual updates, you can exactly set the sampling rate you want. However, even with full scan, you're not guaranteed to get completely representative statistics. There are simply limitations to what you can represent in a statistics object. I will come to that later. And there are limitations to what SQL Server can find in the logic of statistics update. A statistics update uses a single pass over the data, which means it is limited in what it can track, because while reading the first parts of the table, it doesn't know yet what it will read later. So it needs to try to predict what is interesting and what is not. That algorithm doesn't always work. So sometimes I click too fast. Sometimes you just have unrepresentative statistics and no way to fix it. It's something you have to deal with. Then you have to find other ways to fix your issues. And then we have what I call bad parameter sniffing. I already mentioned parameter sniffing when we talked about the table variable cardinality sniffing. Parameter sniffing by itself is not bad. Parameter sniffing by itself is usually a good process, but there are cases where it runs bad. So, like I mentioned in the demo, if you have parameter sniffing, it means that a stored procedure, when it first executes, creates an execution plan based on the values in the parameters passed in. And then later executions reuse that same execution plan. Now imagine that we have a table with our customers and we are based in India. So most of our customers are in India, but we have some customers around the world. If the first query of the day, when we don't have an execution plan for a specific store procedure yet, happens to be where we are looking for customers in New York, then based on the sniffed parameter of New York and the statistics, the cardinality estimation will produce a low number and we will get an execution plan optimized for the fairly low number of New York customers we have. Then the next user says, now I want an overview of all our customers in Delhi. Well, there's a lot more customers in Delhi because India is our target country. Almost all our countries are in India and Delhi is a pretty big city. So we have a lot of customers there, but SQL Server will reuse the execution plan that was optimized for just a few hundred customers living in New York, and we probably get very bad performance. I'm not going to talk much more than this about bad parameter sniffing. There's a lot of information available on the internet. Other sessions are on that topic, so if you ever run into this, do your reading. It's not in scope for this session, but you should be aware of it. Then another problem we have that can result in bad cardinality estimates is the optimize for hint. The optimize for hint is a hint you can put in a query. Say, hey, I have a variable there, and when creating the execution plan, pretend it's going to be this value. So you can even say, always optimize this for customers in Delhi, even if we pass in New York. That might be a good idea sometimes, but it's also risky because now your estimates will always be based on that hard-coded value, even when your actual value is different. And it's hard-coded in your code, so it doesn't change as your data changes. I once was called in for a customer that had some issues, and in their code I found a query that used a query hint based on a transaction date. And the transaction date was used to find some transaction. It was used in a filter in the query. And there was an optimize for transaction date equals, and then there was a date there that was 2 years old, because that was when they first had some issues. To solve the issues they had, they used this optimize for hint to get better performance. But it was hard-coded. It didn't change in the code. So it was a fairly good hint, but now when I was called in, it was 2 years old. Guess what? They had a retention of 1 year in their data. So all their data was at most 1 year old. And we asked for an execution plan to optimize for a filter on 2 years old. So it always gave us an execution plan with an estimate of 1 row, because the optimizer doesn't like 0. And reality was much more. So that optimize for hint was completely biting them instead of helping them. It helped them for a short time, but then it started to bite them. So be very careful when you are tempted to use the optimize for hint. Statistics are very important when you work with cardinality estimation. They play a central role. So if you want to get more insight in statistics, you can use the statement dbcc show statistics, and then you present the table name, and then the second argument is either the name of the statistics object or the name of an index, because every index gets an accompanying statistics object with the same name. Or you can provide the name of a column for which automatic statistics were created. The name of the automatic statistics does not match the column name, but you don't have to worry about that name. If you provide a column name there, SQL Server will find the name of the auto-created statistics for that column. In this example, it's an index. And if you look at the results, you will see that you get 3 result sets back if you run dbcc show statistics, and the first one is called the statistics header. It contains information about the statistics object itself, and about when it was last updated and what we found. So some of the columns you see are here, and one of them is rows. That column represents the total number of rows in the table at the time of the last update. This is always the exact number when the last update ran. It is not an estimation, it is the exact number because it's based on data in internal system tables. There's also a column called rows sample, which shows how many rows the logic looked at to come up with the statistics. In this case, they're the same, so it used a full scan. We looked at everything in the table, which is the best way to get as much detail as you can. But if you have a 10 billion row table, that takes a lot of time, and you might have a much lower number of rows sampled. The difference between these two numbers gives a fair indication of how representative the statistics might be. There's also a column called update, and then that's the last update of this statistics. I created this screenshot quite some time ago. If I have a statistics today that has updated date in 2019, I would be very worried. That's very stale, very outdated, and unless this is a read-only table, I would not like this. For a read-only table, this is of course can be perfectly fine. Once the last update is there, you never need to update your statistics anymore because nothing changes. But if changes have been done since August 20, 2019, they will not be reflected in this statistics, and that's important to be aware of. The second results that you get in DBCC show statistics is the so-called density graph. This is one or more rows with information about density. And what does density mean? Well, the number you see here is computed as 1 divided by the number of distinct values for product ID. And it's product ID because that's in the columns column. If you look at one of the other rows, you will see that, for instance, the third row is 1 divided by the count of distinct combination of product ID, sales order ID, and sales order detail ID. Now, why do we get those 3 columns? Because this statistics is for an index on product ID, but it's a non-clustered index, and every non-clustered index also has information about the clustered index, which for this table is on sales order ID, sales order detail ID. So the index is effectively on product ID, sales order detail ID, and we will get 1 row for each left starting subset there, as you see on your screen. If it had been 5 columns in the index plus clustered index, it would have been 5 rows. If I had manually created a 5-column statistics object, we also would have had 5 rows for the first column only, the first 2, etc. And all of them is 1 divided by the count of distinct combinations for those values. We'll see how this is used later. And then the third part of the output of DBCC show statistics is the statistics histogram. And the histogram has up to, but never more than 200 rows. That's simply because of space considerations. A statistics object cannot have more than 200 steps in the histogram, which is also one of the main reasons why they are often not representative. Because if you have a lot of data, then there are more than 200 interesting points in your table, but you can only keep 200 of them in the statistics object. Now let's look at all the columns and how to read that. So let's look at the row number 10 to understand what these values mean. So the column equality rows says, hey, there's a 600 here. That means that when I created this statistics, I think that 600 rows had product ID 738, the range high key. Now in this case, because it was based on a full scan, that means that when it was looking at the data, it actually saw 600 rows with that value 738. If, for instance, the scan percentage had been only 40%, if we had looked at 40% of the data, then it would have meant that, now I need to do some quick math in my head, it saw 240 rows in the 40% of the data it's looked at, and then multiplied that by 2.5 to assume that there are 600 rows in the full percentage, in the full set. So even the equality rows can be a fractional number if the sampling percentage is such that extrapolating from rows seen to total rows in the table results in a fraction. For a full scan, the equality rows will always be an integer number and never have a fraction. Now there's also the range rows column, and to understand the range rows columns, it says we found 995 rows that were between the current and the previous range high key. So they have product ID larger than 726 and less than 738. For that same range, we also have the distinct range rows, which means in those 995 rows, when updating the statistics, we saw 6 distinct values. If you know those two, you can compute that for each of those distinct values, on average, there were 165.83 rows for each of them. And that's the average range rows. So that's how you read the statistics histogram. And remember, these numbers are based on when the statistics were last updated, based on the sampling percentage of the rows seen, and then multiplied by the ratio of that sampling percentage versus the full data in the table to give an approximation of what SQL Server thinks was in the table when the statistics were last updated. But of course, after updating the statistics, the table will continue to change, and this will get more and more out of date. So even the statistics are already often not completely perfect. Now SQL Server will use those statistics in various ways, and when using those statistics there are some very important assumptions that SQL Server makes throughout this usage. The first is the so-called independence assumption. And the independence assumption means SQL Server assumes that predicates are not correlated. This actually is not always used, we will get to that later. The second is the uniformity assumption, and that says values are evenly spread. So if we already saw that in fact when we looked at the density, the histogram, when we saw we have 995 rows for 6 values, so we assume that each of them happens 157 times, that was the number I think, even though in reality one of the values might have happened 2 times and the other might have happened 900 times, but we assume that they are evenly spread. The uniformity assumption is used everywhere where such assumptions can be applied. And then the last 2 assumptions are very similar, so I brush them together in a single line. The containment and the inclusion assumption both can be simplified, put as if you search for a value it will exist. That's often not the case. Sometimes I use a value in my where clause that doesn't exist in my data. But SQL Server will assume that I am not an idiot and only looking for data that exists, even when I don't. Now let's see how all of this gets applied to our queries. So let's start simple. We're grabbing data from a single table with a where clause, and a where clause uses equality on a variable. We don't know what the value in the variable is. Remember, the entire batch is compiled, so even if there is a set statement above this set at product ID is 5 or whatever, that hasn't executed yet. When this query is compiled, SQL Server only knows there is a variable and I do not know what value it is. I only know the data type. Let's assume it's the correct data type. How will SQL Server work here? Well, SQL Server will look at the density graph. It can't use the histogram because it doesn't know what value of product ID it has. So it just looks at the overall distribution. And this is where this uniformity assumption comes in. So the all density value is a representation, is the one divided by the distinct number of product IDs. So that is a representation of how many product IDs there are. That is the starting point. And then it looks at the DMDB partition stats internal table, or actually the underlying system tables. DMDB partition stats is of course a dynamic management view. But it looks at the actual current row count in the table. So it doesn't look at the row count when the statistics was updated, it looks at the current row count. But it assumes that the density is unchanged, and it assumes that everything is equally distributed, so that every product ID value happens exactly the same times. And based on those assumptions, it uses the density, it uses the current number of rows in the table to come up with a prediction that almost 731 rows will match this for whatever value of product ID is passed in. So here we also see this containment assumption. Yes, we expect that the value you pass in will exist. Now if we change this to inequality, and if you look at the screen you will see that equal to has been changed to a larger than. If you change this to inequality, now SQL Server comes up with a different way. We are going to look for data where the product ID is larger than an unknown value. There's no way to come up with a reliable prediction of that, because we do not know whether at product ID will be 1 or a million or somewhere in between. So every value you are going to put here is a weird hard-coded number, and this is just, it's an impossible problem to solve. And what Microsoft did was simply say, okay, we're going to assume it's 30%. So it takes 30%, 0.3, multiplies that with the current row count of the table, and in this case the statistics aren't even used. Let's look at those two in a demo and then quickly move on. Okay. So here we are going to use our estimate demo database. We saw first how it was created, and I'm going to use the query we already saw on the screen. Make sure the execution plan is there, and if you look at the data here, you will indeed see that this estimated number of rows as expected is 730.981. It's a bit incorrect in this case, but based on the assumptions, this is where we are. The reason it's so completely wrong is that the uniformity assumption, it does not apply here. We don't have approximately the same rows for all products. But SQL Server doesn't know that. It doesn't use that. Now it gets in, we can play a bit with this to do some weird stuff. So I'm going to create a table that has 1,000 rows, 999 of them have the value 1, and 1 of them has the value 2. Then I'm going to create the best statistics I can, with full scan. So the statistics are a perfect description of this table. So if SQL Server really looks at the statistics, it knows that the uniformity assumption is completely incorrect in this case. But SQL Server doesn't verify that the uniformity assumption is always used, and the estimate is still, there are 2 distinct values, you're returning data for 1 of them, so the estimate is the half of the table, 500 rows will be returned, even though in reality it's almost the entire table. And if we do the same for the value 2, then the reality will be 1, but the estimate is still, oh, I zoomed wrong because I didn't check. The estimate is still 500, even though in reality it's now 1. The uniformity assumption is in full swing here. And remember, SQL Server doesn't know what at data will be when it compiles the execution plan. Now, if I look at inequality with a variable, then you will also see that whether I put in 820 or 2000 or 0, the actual numbers will of course be widely different. If you look at the execution plans, you will also see that the actual numbers can be, in this case, 280,000. In the second case, the actual number is 0. In the third case, let's scroll down a bit. The actual number of rows is 345, but in all 3 cases, I didn't highlight it, but you can rewind the recording if you don't believe me. In all 3 cases, the estimate was 103,000, 30% of the table, period. That's all it does. And again, even if SQL Server knows that there's just 2 distinct values, it will still use this 30% estimate simply because it doesn't do anything else. It's simply the hard-coded model, 30%. That's the assumption we're going to make always. So now we're going to compare not with an unknown variable, but with a constant value or with a sniffed value if parameter sniffing is in play, or if we have an option recompile so that the variable can be sniffed. In the demo, I'm going to use a hard-coded value, but all of those 3 cases, parameter sniffing and option recompile with a variable also mean that SQL Server can use the actual value. So whatever the query, we know that we're going to grab data from our demo table for product ID equals to 738. Now we can use the statistics histogram. So SQL Server checks the histogram and says, hey, I have a row where the range high key matches the value I'm looking for. So now I know that at the time I created the statistics, based on our sampling rate, I assume that at that time 600 rows in the table had value 738. Since then the table has changed. In this case, in our demo, we removed 5% of the data. So what SQL Server does now is it says I need to scale down. So it multiplies and divides by the current number of rows and the number of rows when the statistics were updated. So this gives the ratio of rows in the table now versus rows in the table when the last update ran. And as you see, there's this very small rounding error. But 20% of the data has been deleted. SQL Server again assumes that that deletion was also completely uniform, so that also 20% of product ID 738 was deleted. That might or might not be correct, but that's how cardinality estimation works. It assumes this and we don't know whether it's correct. But it scales down or scales up by the same ratio that the table has been scaled down or scaled up since the last update. Now what happens if we are not looking for 738 but for 737? That value is not in the histogram. So how are we going to fix that? Well, SQL Server looks at the range rows, because now we see this is a value that happens to be in the range between 726 and 738. We assume, remember those assumptions, that this specific value is one of the distinct values that exists in this range. And based on that assumption, plus the uniformity assumption that each of those 6 will have exact equal part of the 995 rows, all those assumptions combined means that SQL Server now says, when I last updated the statistics, based on extrapolation from the sampling rate, I assume that 165.833 rows had the value 737 in the product ID column. Now we added or removed some rows since, in our case 20% removal, so again compensate for that, and the final estimation is 157.542. Let's see this in a demo, and that is not just to show that this actually does what I say. Well, let's start there. These are the 2 examples I showed, and you will see in the execution plan that for the first one, the estimate is indeed 570.001, and for the second, the estimate is indeed 157.542. The numbers I showed on the screen, just on the slide deck just before. That's not the most interesting part. Let's play some tricks with the inclusion assumption, because that's where it gets fun. So remember, let's return to the execution plan. If I look for 737, I expect 157.5 rows. Now there are more values in the same range, and SQL Server will assume that they both exist. So if I do in 736, 737, SQL Server will assume they both exist. And let's just look at only the execution plan here. It will come up with an estimate of 315, 2 times the 157, because it assumes 157 for the first and 157 for the second. Now there are 6 distinct values in this range. So if I go for all 6 values, the range has more values, but if I go for 6 values, then the estimate will be up to 945, which is almost everything in that range. This is where it gets interesting. If I now do even more, SQL Server will not, this is 11 values, will SQL Server come up with 11 times 157 as the estimate? No, it doesn't. because it knows that it can never be more than the total range rows. So as the number of values within the range that we are all looking for approaches the number of distinct values, it will start to take that into account and lower the expectation of how many rows there will be for each value, because SQL Server realizes, based on the inclusion assumption and the uniformity assumption, I should expect 157 for this, 157 for this, etc. But there's also only 6 distinct values, so they can't all match the inclusion assumption, and SQL Server starts to compensate for that. On the old cardinality estimator, this worked a bit different. And there you would actually get an estimate that exceeded the number of rows in the range. So there the formula was not as good as it is on the new cardinality estimation. So how about inequality? How about we do a comparison with product ID is larger than or equal to 1189. Now I use a larger number because now I show the end of the statistics histogram, the last few steps. And I have good reason for that, as you will understand. When SQL Server has to do this, it looks at the histogram and it says, okay, 1189, I can find that in the histogram. How many rows do I expect based on the statistics as they were extrapolated when I updated the statistics? I expect that all the rows that are equality rows for 1189, 150, they match larger than or equal to 1189. I also expect all the equality rows and all the range rows for everything above that to be there. The 880 range rows for the range high key 1189 will not be there because they describe the range up to 1189. So all those values are added together. 3131 would be the estimate based on the statistics as they were extrapolated when last updated. We're going to compensate for how many rows were added and removed, and now we have a value of 2974. And that's the estimate. Change larger than or equal to just larger than. How does this change? Well, that's quite simple. These equality rows no longer match because we look for larger than 1189. So those 150 rows are simply removed from the formula, and there's your new number. That's all there is to it. But of course, in this case, we were lucky because we are looking for a number larger than 1189, which happens to be a range high key. What if we're looking for larger than 1191? Now it gets a bit more complex, but let's start with the easy part. We are somewhere in the range between 1197 and 1189. So what we know for sure is that everything equal to 1197 matches, and everything in the ranges and equality above that, so the entire rest of the histogram, is also there. But this isn't the complete prediction yet, because this will be larger than 1197. So we still have those 1134 range rows, which describe the range between 1189 and 1197. We assume uniform distribution. And 1191 is approximately at 30% of the range between 1189 and 1197. So that means that we expect that approximately 70% of those 1134 range rows will match. And on your slide you will see that I use an approximation symbol because this 70% is not an estimation done by the cardinality estimator. This is an estimation done by me of what I think the cardinality estimator will do. So the cardinality estimator will try to divide the range between 1189 and 1197 based on the search value 1191. I think it will be close to 70%, but in reality I might be wrong as well. If I'm completely right, then the final result should be, after compensating for how many rows were added and deleted, 2508.764. In the demo you will see that the actual number is 2502, which means that in reality SQL Server didn't use 70% but something like 69.8% or something. Close enough. I think I did a fair, good job of predicting what the optimizer would do, what the cardinality estimator would do. Now again I made a very small change. I went back to larger than or equal to. The only thing that changes now is that instead of 70% it will be more like 86%. Based on my estimation of 86%, it would have been 2681. In reality, it's 2682. So again, I was off by a tiny bit. It's 86.1% or so. Well done, Hugo. Let's quickly look at these demos. And then we'll move on to more interesting stuff. So we're just going to execute this. This is not the most exciting demo. I'm just going to show you that all the numbers I showed before, 2974.45. And then when we remove the equality, it goes up to 2831.95. As it goes up, I meant goes down, of course. And then when we use 1191, the estimates change to 2502.78. And finally, that was the one I already showed. I need to go to this one, 2682.33. Not very interesting, but good to know that I actually got it all right on my slides. Now, all of this used a single predicate only. In reality, most of the time when we query, we have more than one predicate. And up to SQL Server 2012, this would be where the independency assumption goes into full swing. Independency assumption means that if there are, for instance, two tests, we assume they are tests like lives in India and is male. There is no reason to believe that India has a higher or lower proportion of males than any other country in the world. So those are in fact independent. If you if you have a table that is 50% males, 50% females, and you filter on male only, you get half of the table. If you filter on India and then filter on males only, you get half of the people in India. So in a case like that, it would be correct. But not everything is always independent. If you have things like lives in India and is a Buddhist, then there's partial independency. Not all people in India are Buddhists. Not all Buddhists live in India. But there's no doubt that India has a much higher proportion of Buddhists than, for instance, Germany or Denmark or America. And if you go as far as lives in India and lives in the city Bangkok, well, yeah, that's full dependency, because Bangkok is part of India. So you can just skip the filter on India, and everyone who lives in Bangkok always lives in India. But for SQL Server 2012 and before, independency was assumed. And that means if you look at how it works, SQL Server will first estimate the selectivity using the methods I just described to determine the selectivity of each predicate. And the selectivity is estimated number of rows divided by the estimated number of rows in the table. So the percentage of rows that remains after that filter. It then finds the combined selectivity by simply multiplying all of them, and then the row count is that combined selectivity multiplied by the table cardinality. Let's look at an example. So we have three conditions. We have a table with 100,000 rows, and if we filter on column 1 equals to A, the estimate is 4,500 rows, which means a selectivity of 4.5%, 0.045. Based on the density, where column 2 equals add variable 2, gives us a density of 0.025, which means the selectivity is 0.025, and the third one uses inequality, where the selectivity is always hard-coded 30%, 0.3. With those three predicates, if we use a query where those three are tied together with AND, the combined selectivity will be the product of 0.005, 0.025 and 0.3 for a combined selectivity of 0.000335 and an estimate of 33.75 rows. In SQL Server 2014, the assumption changed to partially dependent. Partially dependent means SQL Server assumes it's like living in India and being a Buddhist. it's not fully correlated. It's also not fully independent. There's a partial dependency. And what SQL Server does here is it starts with estimating the selectivity of each predicate. That's the same. That's not changed. But now, once it has all the selectivities, it sorts them in order of ascending value. So the most selective selectivity comes first. If based on the data in our table, which is not the world population, but our table, if based on the data in our table, 50% of the data in our table is living in India and 20% of the data, let's say 60% of the data living in our table is Buddhist, then living in India will be the most selective selectivity. And remember, if 60% of our people are Buddhist, then using that filter removes 40% of the rows. But now it will start by assuming, okay, selectivity 1 living in India, 50%, that's going to be used unchanged. But then the second selectivity of 60% is no longer 60% when we look at India only, because it's partially dependent. It's going to use the square root of 0.6, which is a higher number, 0.8 or something like that. I didn't do the math. So now we filter less. And that's logical, because if you have the population of India and you filter on Buddhists, you don't remove as many rows as when you apply Buddhists on the entire data. And so every selectivity is square rooted one more time, and that's called exponential backoff. And the result is then used to find the row count in the same way. Now, with the same example we had before, 0.045, 0.025, and 0.3, you can see on the screen, after doing the ascending order using the square root, square root and double square root, the estimate will be 392, which is over 10 times as much, because now we assume that there's partial correlation between the filters. On SQL Server 7 to SQL Server 2012, there's also an alternative way to predict the cardinality when there are multiple predicates. And that is if there are multi-column statistics. They are never created automatically. You have to create them manually. But if they exist, then SQL Server will use the average density for the column combination and not look at the statistics histogram. In SQL Server 2014 this was removed, and that turned out to be an error because in SQL Server 2016 it was reintroduced. So here that concludes the filters. Let's move to joins for the last of this talk. When we join two tables, it gets really interesting. And this is where most of the stuff that is documented stops. Microsoft hasn't documented much here. So this is where we get really deep. And I'll try to explain as good as possible. But let's start with the simplest of joins on a single equality predicate. How does this work? Let's look at the table, at the demo. So let's first look at the statistics, and I'm going to go briefly, but the first statistic between, I'm only looking at this range between 750 and 760. So for the demo table 1, which had correct statistics and then lost some of our rows, this is the relevant part of the statistics. And don't try to memorize it. I have replicated it on the slides. I just show it here. And then for the demo table, demo table 2, we have the same data, but the statistics were created later. And here the statistics are therefore in 4 rows, because now the data was different. Based on those statistics, we already talked about, let's do it like this, the various ways SQL Server uses, and actually I didn't cover the between, but that results in some estimates, and they're fairly correct. If you look at the two, they're not far off, but we're not looking at that anymore. We're looking at what happens when I do a join. And in this case, I'm going to use the SQL Server 2012, the legacy cardinality estimator. We'll return to SQL Server 2014 later, but we'll start with legacy in this case. Now I only look at 750 and 760. I'm going to join the two. And if I look at the execution plan, then obviously there is this estimate of 3,327 for demo table 1 and this estimate of 3,327 also for demo table 2. We already saw that. We don't care about that anymore. What I now want to look at is this estimate of 1,182,660 rows. Where does that estimate come from? Let's look. So we start with the histograms, and I'm representing the histogram here. So what you see here is for demo table 1, the value 750 had an equality, and there were 358 rows according to the statistics. 754 and 760 also had 226 and 680 rows. And then for the two ranges, the first range from 750 to 754 had 3 distinct values and 1262 values total. And the second had 5 distinct values and 961 values total. So that's how you should read this data. These values are all taken from the DBCC show statistics I ran in the demo. And the second graph is similar, but well, it uses the same method, but of course the values are different because the second table had a different statistics histogram. Now let's move this up a bit to make place for the rest. So we have the two histograms, and SQL Server will align them. That means it runs through all the relevant parts. So when trying to predict the number of rows in the join, it will look at each segment of the two histograms after layering them on top of each other. So for example, it looks at the value 750. That's a simple one. Based on the statistics, we expect 358 rows in demo table 1, 336 rows for the same value 750 in demo table 2. Obviously, if we join, all of those will match on product ID equal product ID. So this is a prediction of 120,288 rows in our results on the join from just the value 750. For the value 760, which also is an equality value in both histograms, the same method is used, just with a different number. Now there's also 3 values that have an exact value in one of the histogram, but don't have an exact value in the other, like for instance the value 750. We know based on statistics that we expect 356 rows with that value in demo table 2. For demo table 1, we are going to use the containment assumption and say, okay, this value 752 will probably be one of those 3 distinct values in that range. So that means that based on the uniformity assumption, 1262 divided by 3 values will be found in demo table 1 for 752. We multiply that by the 356 in demo table 2 for approximately 150,000. That same logic is then used for 754 and 757 because those two have an equality value in one of the two histograms and not in the second histogram. But that's not all yet, because we still have this range between 750 and 752. And before you say, oh, that's one value, it's 751, SQL Server doesn't assume it's integers. SQL Server has a simple mathematical model that is always applied regardless of whether it's integers, as is the case here, or real values or decimals or anything else. So SQL Server cannot simply say, oh, there's only one value there. But what it can do is say, okay, this range from 750 to 754, I'm looking at the value 752, so that's approximately 50% will be less than 752 and more than 750. There are 3 distinct values in this range, but one of them I already used for the match to 752. So there's 2 distinct values remaining that are not equal to 752. And well, those I expect that 50% will be less than 752. So in this case, the number is actually going to be approximately 1, but not because of the logic of, oh, that's the only integer value there. Those approximately 1 distinct values, and here I once more use the approximate effect because I have estimated the interpolation between 750 and 754 to do 50%, but I'm not entirely sure whether it's actually that value. But I think the optimizer will use approximately 50%. Now it has 1 distinct values in the top histogram. In the bottom histogram it has exactly 1 values because here we have this entire range. We don't need to do any mathematics, we have this range. So now it computes 1 value in both histograms. It will match 11, 20, 62 divided by 3 times in the demo table 1, 389 divided by 1 times in demo table 2, and there we have an approximation of 163,600 something rows for this range. And for the second range it uses something similar, but now we have to interpolate in both cases. So for the demo table 1 it's again approximately 50% of the 2 remaining values, but for the bottom value it's, and here how does 752 to 757 interpolate when you do only up to 754? I think it will be approximately 40%, but the estimator might use something different. And again, it multiplies by 3 because the value 754 itself has already been consumed. So of the 4 distinct values in the range, of these 4 distinct values, this one has taken, so 3 remain. And that's 1.2 distinct values. And now you see that there is a mismatch between the number of distinct values in demo table 1 and the number of distinct values in demo table 2. And now something interesting happens, because we have all those assumptions that values exist. But the estimator is not stupid. The optimizer will say, hey, this number is lower than this number. So these 0.2 additional values can never match in an inner join. The number of rows in the join result can never, the number of distinct values in the join result can never be more, for an inner join that we're looking at here, than the number of distinct values that we have here. So some of these values will not have matches and will be lost. Sorry, that's how it is. But I'm going to use the lowest of the number of distinct values as the assumed number of distinct values in the result. And for those distinct values, it will then come up with 1262 divided by 3 for this area, 987 divided by 4 for this area, and then we have our result 104,000. I'm rounding it a bit. Again, the same method is used for the next interval, and again we have a 1.8 and a 2 in my approximation of how the cardinality estimator will approximate things. The lowest of the 2 distinct values is used for 1.8, and the fourth step matches the first more or less, where one has to be interpolated, the other is exact. All those values are then added together and then scaled up or down for the changes in how many rows were in the statistics when we updated the statistics and how many there are now for both demo table 1 and demo table 2. And based on my expectation of how the cardinality estimator does its interpolation, I expect 1,177,637.3 rows to be the estimate. In reality, we saw that in the demo it's 1,182,660. The difference here is because my interpolations of 50% and 60% and 40% were off by a bit from what the cardinality estimator actually uses. But it's close enough that I believe that this is correct. Now on SQL Server 2014, this process changed. On SQL Server 2014, a new thing was introduced, and this was documented. It was called simplified histograms, and there was a short description saying that everything in between the first and last value will be added together and changed by a single, replaced by a single range. So how does that work? Well, everything between 750 and 760 for the first histogram for demo table 1 is added together. So we have 3 distinct values here. We have 1 distinct value equal to 226, and we have 5 distinct values in this range. We add them together for 9 distinct values. We have 1260 rows, 1262 rows here, 750 rows for value 226, and 961 rows for the second range. Add that together for 2449 rows. And now internally, the histogram, the statistics itself will not be changed, but internally, for the cardinality estimation, it will in memory use a fake histogram that pretends this is all a single range. It will do the same for demo table 2. And now we have 2 simplified histograms. And based on what I read on the internet, this is how I expected it to work. But watch, it's not entirely correct. We'll get there. Let's first see what would happen if this was actually reality. Again, we have the simple match for the values 750 and 760, same as the simple matches for the SQL Server 2012 version. And then we have a single range to do using the same method as before, but now there's no interpolation anymore. So now we can trust that this is actually the value we get. You do not see the tilde symbol I used before to signify that I had to estimate what the cardinality estimator did. So this should match reality. But if we do this in the demo, you will see that the actual estimate is much lower. And that means that how I thought I should interpret the histogram simplification was incorrect. And when I ran into this, I had to do some experiments, and based on things I tried and some mathematics I did and some other stuff, I eventually worked out I misunderstood, or Microsoft misdescribed, how histogram simplification works. So in reality, it doesn't create a simplified histogram of a starting point, an ending point, and a range in between. In reality, it works with a simplified histogram of a starting point and a range from above the starting point until the end point, including the end point. So it wouldn't be 2044-9 with 9 distinct values. No, these 760 rows will be added there, and this single distinct values will be added there. So it will be 10 distinct values and 3,209 values, if I do the math correct out of my head. I didn't change the histogram on the screen, but I showed the logic here that now what actually happens is that the point 750 is still considered a simple point, which is the start value, but it doesn't use 2, 3, 4, 4, 9 and 9, but it uses 3,129 and 10. 2, 4, 4, 9 plus 760 and 9 plus 1. And the same for the second histogram. And if you now do the numbers, I ran the math, I come up with an expected estimate of 1,003,364.9. Look in the execution plan, 1,003,360. That's not an exact match, but I happen to know that estimates in execution plans are always rounded to 6 significant digits. So this 4.9 here is rounded down, and we have an exact match. This is how a join cardinality estimation works in SQL Server 2014. Okay, fair enough. Let's move on. Let's also look at an inequality predicate. You may not do this type of join very often, but it's legal, and I want to know how SQL Server handles it. This is not documented at all. Nothing. So, room for speculation, right? Let's move to SQL Server old cardinality estimator up to 2012 and run a variation on the equality algorithm. Let's assume it uses the same logic of aligning histograms. Now, if you approach this logically, you can see how it should work. Because we know that there are 350 rows, well, we don't know, we assume based on statistics that there's 358 rows in demo table 1 that have value 750. We join on demo table 2 is larger than demo table 1, so that means that these 336 rows do not match, but all the others do. So we can simply add all those rows together, and we know that the 358 750s in demo table 1 will join to the 2,991 values larger than 750 in demo table 2. That's a large number. And that's only the 750s. So now the range from just above 750, again we don't assume integers, to just before 752. There's again this 50% interpolation, that's my interpolation, not the cardinality estimators. Cardinality estimator will be close there, but not exactly. So we assume 631 rows will have a value between 750 and 752. Now those rows will definitely match with the larger than test, all the rows of 752 and larger. So that's the easy part, 631 multiplied by 2602. But that's not all, because we also have 389 rows that also are in the range between 750 and 752 in demo table 2. They will not all match, but some of them will. Based on the uniformity assumption, it should be about half. So now we have 631 multiplied by 2602 because there's larger values, and then for the overlapping range 631 times 389 times 0.5 because half of them will be larger, half of them will not be. That's another large number and we add it to our total. And now we'll continue like this. For 752 once more, this matches everything larger and no weird stuff with overlapping intervals because it's an exact value. Then we have an interval again using the same method of half of the interval will match. Yes, it's a complex formula you see up there, but this is how it works. And I'll quickly tap through it. You can watch the slides later. You will see that all of this step by step uses the same methods every time until finally we get at the value 760 and those 680 rows will not match anything based on larger than, so we add 0. This is the large number based on the statistics. We have to compensate again for rows added or removed after the statistics update. And we have our final estimate of 6 million and a bit. I'm not going to show it in the demo, but you have the code, you can do it yourself. The actual estimate is much lower. For now, I'm going to assume that this is based on my assumptions of 60%, 40%, 50% not being completely correct. Even though the difference is quite large, but based on the formulas here, small difference in those assumptions do get large effects. So I'm going to give myself this freedom of assuming this is correct. But I have a good way to double check because in the SQL Server 2014 version, we used the simplified histogram. So the simplified histogram can also be used for this same logic and it's again easier. And remember, with the simplified histogram, I didn't have to make any assumptions. So now we can check for an exact match to see whether my theory, because all of this is a theory, this is not documented. My theory, I can now really verify it without having to work around my own assumptions, my own approximations, I'm sorry. So based on the simplified histogram, the 358 rows with value 750 should match the 2991 rows with values larger than 750. And then we have the single range for everything above 750 that matches half of that same range in the second table. Add those together and we expect that on SQL Server 2014, the estimate, if my idea of how this inequality works is correct, then I expect an estimated cardinality of 5,750,000 and a bit. I ran the, I forgot to scale down and up for changes since the last statistics update and I expect 5,462,000 and a bit. I ran the query, it's in the demo code, you can check it for yourself. The actual estimate is that exact number rounded to 6 digits. So this confirms that definitely for SQL Server 2014, this method is used to predict the number of rows returned from a join based on the simplified histogram. And that reinforces my theory that my assumption for SQL Server 2012 was also correct. I was just incorrect in my approximations of the 40, 50 and 60% that I used in the slides. That's a lot, I realize. And we're not there yet. There's even more to come. So what if we join on not a single condition, but a second condition as well? This makes it even more interesting. And again, there's a difference between the old cardinality estimator and the new cardinality estimator. So for the old cardinality estimator, what SQL Server would do was first compute the selectivity for each predicate. Meaning it would do a cardinality estimation for a join on only product ID. And then it would do a cardinality estimation for a join on only sales order ID, detail ID. Then it would multiply the two selectivities and assuming that they're independent. Again, this independence assumption. So let's look at this in detail. And I did not run the math for this for myself. I simply ran asked for the execution plan for the Cartesian product, and the estimated Cartesian product is 119,546,000,000 rows, simply the product of the two table sizes. If we join on product ID only, and again, I could have done all the steps by hand, but in reality I just looked at the execution plan for a query based on only a product ID test in the join. There, the estimate was 536.8 million rows. If I join, that means that the selectivity of a join on product ID only is 0.004491. Only 0.44% of the rows from the Cartesian product survive if I join on product ID. Then I ran, or rather asked for an execution plan for a join on only sales order ID, and there the estimate was 0.985 million. So here the selectivity is even higher. It's 0.00008246. So most of the rows from the Cartesian product are immediately removed when I add a join on sales order detail ID equality. SQL Server assumes that the product ID and the sales order detail ID join conditions are not in any way related. It assumes independence. So now it says the combined selectivity, if I join on both, is 0.0. Well, I'm not going to read the number. You can see it on the screen. This intensely low number, very selective. And that means that if I apply that very high selectivity to the assumed Cartesian product of 119.5 billion rows, I'm going to come up with an estimate of 4,427 rows. The actual estimate when I ran this query was 4,427.23, and that's just rounding errors. However, if there is a multi-column statistics on product ID plus sales order detail ID, or there is an index on those two columns, or those and more, then it will use the density for the column combination from the density graph. It uses that density to come up with the estimated number of distinct product ID and sales order detail ID combinations in both tables. It uses the lowest of the two, because that's the maximum number of distinct combinations it can have in the results. And then it says those two combinations, using the uniformity assumptions, I can compute that for each of them, for each value in those of those 345,492 rows, I can use the density again for D1 and D2 to come up that for each row in demo table 1 there will be 1.0009 rows with that value, and for the demo table 2 it's 1.0008. Now we assume that all of those 3,492 rows will be in the result set, but not again the higher 345,754 from demo table 1, because the rest simply has no matches in demo table 2. And for each of them, there will be 1.0009 in demo table 1, 1.0008 in demo table 2, and there's your final result. And again, the actual estimate was close enough that I believe this is rounding error, because I only started with already rounded numbers from histogram and from execution plans. Now in SQL Server 2014, this join method has a very different method for cardinality estimation, because this whole method of computing the selectivity for each individual predicate and then multiplying and then applying that to the Cartesian product does not exist on the new cardinality estimator. In reality, SQL Server 2014 and beyond will always use the method of using the density for the column combination. So the same as SQL Server 2012 with multi-column statistics. It's the only method. However, this does mean that if there are no multi-column statistics, it has to do an approximation of the multi-column density based on the 2 or more single column densities that it does have. And that's a bit beyond the scope. I do not have time to go into the details of that. Now, small change in the query, I combine equality with inequality. I'm just going to continue increasing the level over and over again until everyone's brain is exploded. I hope you're fine with that. So in the old cardinality estimator, the method is still the same. Compute selectivity for each predicate, multiply assuming independence, same as for two equality predicates. Here the multi-column statistics are not used because they are useless when we use inequality rather than equality. So that's simple. SQL Server 2014 and beyond only used the density graph. That's useless with inequality. So now we have to go to a different method. But now we have yet another different method. So for SQL Server 2014 and beyond, SQL Server would estimate the cardinality of each input. So it doesn't look at the join condition. It only looks at how many rows are there in demo table 1 and how many rows are there in demo table 2. And it says because there's inequality, I will assume that the larger of the two inputs will have one matching row in the smaller of the two inputs. Is that assumption correct or not? I don't know. It completely depends on your use case. In some cases it will be correct. In some cases it will be too high. In some cases it will be too low. Remember, I said it at the start, and I'm going to repeat it, estimates are always wrong. What Microsoft does is try to come up with estimates that are not too far off and that are not too bad and that are at least as correct as possible in cases where it matters. But it's always going to fail. It's never going to be always correct. And especially in weird cases like this, whatever your assumption is, if it matches your reality, you will be happy with the estimate. If your reality is completely different, you will get a terrible estimate. That's simply a matter of life that we as DBAs and SQL developers have to be aware of and have to work around. The last example I'm going to show is when we join. In this case I'm going back to a join on a single condition, but there is also additional filters. So we're starting to approach actual realistic queries. I mean, still simpler than most of the queries I have, but we're getting to some level of realism finally. And I'm going to go through this pretty broadly because this is just a combination of stuff we had before, but they're combined in very interesting different ways. And here's a weird thing. On the old cardinality estimation, we always had the independence assumption, except in this case. In this case, the old cardinality estimator suddenly said, no, now I'm going to assume that the filters are correlated, that your filter on demo table 1 somehow correlates with your filter on demo table 2. And in order to achieve this, the method used internally is that SQL Server will first determine the selectivity of d1.sales order detail ID is larger than 15. And let's say that's 20%, so 20% of the rows match that filter. Then it will scale down the histogram on demo table 1 by 20%. So all the values in that histogram are reduced to 20% of the values that are actually in the statistics. Basically, the prognosed statistics after filtering on sales order detail ID larger than 15, assuming uniformity, etc., etc. Then for demo table 2 it does the same based on the selectivity of sales order detail ID is less than 20. It scales down that histogram as well. And then it uses the histogram alignment method that I spent a lot of time on before to predict how the two scaled down histograms can be aligned. And that comes up with a number, and I didn't go through all the math myself. I spent a lot of time on this, but not multiple years. Computers do that much faster, so I simply grabbed the execution plan for this query, and as you see, the result of this step is an estimate of 3077.81. Now on the new cardinality estimator there was a small change. Now there's an assumption of no correlation between the filters. And how they did that is to just swap the order a bit. So now they align the original histograms, not scaled down. So they start with an assumption of with an estimation of the join without the where condition, simply as if we're doing it for the entire table. Then SQL Server will determine the filter selectivity for the filter on demo table 1 and the filter on demo table 2, and it will reduce the estimate after this histogram alignment. So we have the estimation for the join without the where, we have the estimation of the selectivity of the where, and then it will reduce the estimate based on the combination of those two selectivities. And now the result is suddenly an estimation of 36,856, so more than 10 times as much. That's all I have time for. There will be a short few minutes left after this to do live Q&A. I hope there were lots of questions during the presentation in the chat window, and I will answer all of them during the delivery. If you have questions later, feel free to mail me, to tweet me. For now, I'm going to say thanks for your attention. Thanks for being here. Enjoy the rest of the Data Platform Virtual Summit 2021. My name is Hugo Kornelis. Thanks for watching. And don't forget, Microsoft has supported Data Platform Geeks and SQL Server Community Geeks and the community initiatives. Thank them if you have the chance. Special thanks to the sponsor. Again, don't forget the ways to win prizes. If you are interested in prizes, post your selfie, give feedback, visit sponsors, follow Twitter. Thanks again. Don't forget to send your questions. My name is Hugo Kornelis. Goodbye.